In this video, I'm gonna talk about my ideas on the topic. But before I do that, do you want to know a book that is key to quantum gravity? It is not the book on string theory. It is not the book on loop quantum gravity. It is the book by Claude Shannon on mathematical theory of communication. It is an engineering book that revolutionized the digital age. But as I explained to you, Johnny von Neumann put it at the center of quantum mechanics, and the recent Nobel Prize of Physics in 2022 was given to Vienna guys for proving entanglement or improving it anyway. So what I'm trying to say is that information will be at the center of physics, and not only information, the concept that is the star of the information theory, the entropy, will be the guiding light in this revolution. But let's come to my ideas, my speculations. What did I tell you? How did Boltzmann revolutionized statistical mechanics? He was able to come up with a new definition that connected two unseemingly unfamiliar fields in physics and connect them via a definition. That definition is a definition of the entropy. So I believe that the entropy content of the universe is constant. Well, you will say, how can you tell that as a physicist? According to second law of thermodynamics, the entropy of the universe has to always increase. You are right. You are exactly right. But there's a force that we don't yet understand, and that force is gravity. That force cannot be united with the other fundamental forces. So you cannot impose, let's say, a definition, a von Neumann entropic definition to gravity, to general relativity. You cannot do that. And do you know what you cannot unite with von Neumann entropy? That is thermodynamic entropy. And Ted Jacobson in 1980s have come up with a formulation to derive Einstein's equations from thermodynamic axioms. So by imposing a thermodynamic system, like second law of thermodynamics, and as well as a cutoff, the smallest length for a space-time that is actually related to Hawking's radiation, you can come up with Einstein's field equation. So it's an alternative derivation of Einstein's equations via using thermodynamic laws, without using Lagrangian. And this is a revolution because you cannot do that with other theories. So you see, we have three different unrelated mountains in physics. The one is, let's say, the theories that are bred with quantum mechanics, and the other one is statistical mechanics, and the other is classical general relativity. Jacobson showed us that one can obtain the equations of general relativity using the postulates of statistical mechanics. Doesn't this telling you something? This is telling us that these two fields are fundamentally connected. And as I told you in the previous video, the part 1 of this video as well, it is the thermodynamic entropy that dictates the flow of time. So if we had only Johnny von Neumann's entropy, since every evolution in quantum mechanics is unitary, the entropy content of the universe would be constant. But since we have a thermodynamic entropy, and since we have the second law of thermodynamics, it necessarily introduces an antisymmetry to the cosmos. And this is exactly what we call as the flow of time. And this is the only law of physics that tells us that there's a flow of time. And this observation has been made for centuries. There's a book by Planck, I think it is called The Characteristic of the Physical Law. And in it, Planck was fascinated with the second law of thermodynamics and how it was at the center, and how it is something that is fundamental, and it's like an external axiom to all the physical laws. So this fascination, this wonder about this concept has been going on for centuries, and it is not yet resolved. And many physicists aren't really aware of this. So what I'm trying to tell you is that we are observing a fundamental similarity between classical general relativity and thermodynamics. But we need a new definition. As I'm telling you, Johnny von Neumann's entropy isn't something that is connected fundamentally to statistical entropy. But statistical entropy can somehow give a rise to classical general relativity with other thermodynamic axioms. But what I'm trying to say is that we need a broader definition of entropy. We need to introduce a concept that could unify all these other islands that are disconnected from each other. And the way to do that with another postulation, like Boltzmann did to thermodynamics by introducing the statistical definition of entropy. One needs to introduce, I think, a definition of entropy to classical general relativity. And if you look at the evolution of the universe and how the cosmos has come to be, the stars formed and like beautiful. So when the universe started, there was an explosion, the highest entropy, let's say the highest chaos that is possible. And over time, we observed order. Yes, the second law of thermodynamics says that everything needs to be more disordered. But if that's so, how can we observe these beautiful stars in our galaxy? How can we living organisms have come up to be? And there's a beautiful argument in Schrödinger's book, What is Life, that is about it. He connects the definition of life and how metabolism is able to maintain itself to the laws of entropy. So what I'm trying to say is that if there were no counter force, let's say counterweight to entropy, if there were nothing that could counterbalance the increase of entropy in the universe, we wouldn't observe any living thing. We didn't observe any structured phenomena, but we observe it. And the key to the negative entropy in this case is gravity. Without gravity, those particles that created stars, those cells that are able to absorb the sunlight, which is the fundamental driving force, the driving energy for the existence of life, wouldn't exist. So what I'm trying to say to you, gravity is what is opposing to thermodynamic entropy. So this is another speculation that I'm making. I am postulating that the entropy of the universe is constant. Yes, you heard me right, it is constant. Thermodynamic entropy is counteracted by gravitational entropy that I am yet to develop. But how could we quantify entropy in a classical general relativity? That is the question. That is the key to our solution. Well, in order to examine this mathematically, I had several ideas. Well, we need to look at how the gravitational, let's say, evolution at its smallest scale, maybe through twists and curls, could be related to entropy. And to do that, you need a scholar. And how can maybe one needs to introduce, let's say, we shouldn't look at what we always look at through the lens of classical GR. Maybe we need additional mathematical tools from algebraic geometry to introduce some statistical aspects to the smooth manifold that we are dealing with. So I have some couple of ideas to attack this problem that I'm developing, but I'm sure that this is the key. So thank you for your time and stay with physics.